3i Atlas has cornered NASA, the most powerful space agency on Earth, in a crisis spiraling beyond its control. Every telescope is trained on it, every government is watching, and yet, NASA has vanished behind silence. The data exists, the images exist, but the access, sealed tight behind a phrase that sounds harmless, NASA-wide news lockdown. Harmless until you realize it means total blackout. Now, NASA stands on the edge of revelation or ruin. Speak and risk global chaos. Stay silent and confirm every fear they've tried to contain. Because 3i Atlas isn't just defying physics, it's dismantling the illusion of control itself. Stay with me until the end. Because tonight, you'll realize that what NASA isn't saying about 3i Atlas could change our entire understanding of the universe and our place inside it. If this story has you questioning what's really happening above us, don't miss what's coming next. Hit like, subscribe, and drop a comment with where you're watching from, what time it is there, and tell me, do you believe we're hearing the full truth? And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. Cold Open. NASA has the images, the orbiters saw it, but 2 weeks later, silence. You know that feeling when you see something you can't explain, something that makes the hair on the back of your neck stand up? Now imagine you're NASA, and you've got the most powerful telescopes humanity has ever built pointed at an object that shouldn't exist the way it does. You've got the data, you've got the pictures, and you can't say a word. Welcome to the story of 3i Atlas, an interstellar comet that didn't just drop by for a visit. It cornered the world's most powerful space agency into an impossible choice. Let me paint you a picture. It's July 2025. Headlines start appearing everywhere. Interstellar Comet 3i Atlas. Scientists are gathering at symposiums, telescope images are being passed around like trading cards, and astronomers are doing that thing they do when they're excited but trying to stay professional. They're mumbling carefully chosen words into microphones, hedging every statement with preliminary data suggests, and further observation is needed. But if you look closely at those data logs, at the timestamps on the observation records, something weird starts to emerge. Gaps, broken sequences, periods where you'd expect continuous monitoring, but instead, there's just nothing. Radio silence from the agency that's supposed to be humanity's eyes in space. Here's the claim I'm making, and I want you to sit with it for a moment. 3i Atlas didn't just challenge astrophysics. It cornered NASA into a situation where every single move carries catastrophic risk. Think about it like this. If they release too much of what they saw, what happens? Panic. Conspiracy theories that make the moon landing deniers look reasonable. Social media explodes. Cable news runs 24/7 coverage with increasingly breathless speculation. Congressional phone lines light up. Every fringe theory gets amplified until the signal drowns in noise. But if they stay silent, if they keep delaying those releases, if they keep saying the data is under review, if they keep letting weeks slip by while the world watches and waits, their credibility erodes. That precious trust that took decades to build starts crumbling. People start asking the one question that terrifies every scientific institution. What are they hiding? And here's where it gets really interesting. This isn't happening in a vacuum. There's political timing to consider. NASA's funding cycles don't care about cosmic visitors. Congressional oversight hearings are scheduled months in advance. Budget reviews happen whether or not an interstellar object decides to do something unprecedented. The bureaucratic machinery of a massive federal agency doesn't stop just because the universe threw a curveball. Then there are the rules. Oh, the rules. NASA operates under something they call NASA-wide news protocols. When something is flagged with that label, it's not just one department that needs to sign off. It's not just one scientist who needs to verify. It's a whole chain of approvals, clearances, legal reviews, communication strategies. The machine has to grind through its process, and that machine moves at the speed of bureaucracy, not at the speed of a comet screaming through our solar system. The public expects answers. We've gotten used to instant gratification, haven't we? We expect that when something happens in space, NASA tweets about it. They post the images. They hold press conferences. We've been trained to expect transparency, immediate and complete. So when that transparency suddenly isn't there, when the usual flow of information just stops, people notice, and they start to wonder. But here's the thing that should really make you lean forward. What if what NASA saw wasn't just unusual? What if it was more than a comet? What if their telescopes captured something that doesn't fit into any comfortable category we've created for cosmic objects? I want you to feel the weight of that question. Because somewhere in a building in Houston or Pasadena or Washington, someone is sitting with that exact dilemma. They've seen the images, they know what the data shows, and they have to decide what to do with information that could change how humanity thinks about our place in the universe. This is about the fear of the unknown, yes, but it's also about the power of secrecy, about what happens when the people who are supposed to tell us the truth find themselves unable to do so without causing chaos. It's about the collision between scientific responsibility and institutional survival. You want to know the real story? It's not in the press releases. It's not in the carefully worded statements from NASA Public Affairs. The real story is in what they won't show you, in the images that haven't been released, in the data that's sitting in review queues, in the conversations happening behind closed doors where someone is trying to figure out how to explain the inexplicable without setting off a panic. Every space agency has protocols for unexpected discoveries. They have flowcharts and decision trees and chains of command. But those protocols were designed for a world where anomalies fit into predictable categories. Equipment malfunction, unexpected asteroid, interesting but explainable phenomenon. They weren't designed for something that breaks the rules so thoroughly that you can't even be sure what category it belongs in. So here we are. NASA has the evidence. The world is watching. The clock is ticking, and every day that passes without a full disclosure, the tension ratchets up another notch. What happens when the institution responsible for revealing the wonders of the cosmos becomes the institution suspected of hiding them? What they won't show you, that's the real story, and we're about to dive into exactly what that hidden timeline looks like. Part 2, What the Public Doesn't See. Let's go back to the beginning. July 2025. The Atlas survey, that's the Asteroid Terrestrial Impact Last Alert System, picks up something in their automated scans. It's transient object, which in astronomy speak just means something that wasn't there before and probably won't be there long. At first it's just a blip, a data point, one of thousands that the survey catalogues every month. But this one is different. Within 48 hours, someone notices that the trajectory doesn't look right. It's not moving like something that belongs to our solar system. The orbital parameters are all wrong. It's moving too fast, and more importantly, it's moving on a hyperbolic path. That's the technical way of saying it came from somewhere else, interstellar. Now, interstellar objects aren't completely unprecedented. We've had visitors before, but they're rare enough that when one shows up, the entire astronomical community pays attention. So the word goes out. Gemini Observatory points their telescopes at it. Hubble gets scheduled time. The European Space Agency's ExoMars mission has a camera called CASSES, and they swing it around to take a look. Within a week, you've got some of the most powerful instruments humanity has ever built, all focused on this one object. And that's when things get interesting, because if you start tracking the public release dates, if you map out who posted what and when, you start to see a pattern. Or rather, you start to see the absence of a pattern where there should be one. ESO releases their first images on July 23rd. Gemini Observatory posts their data 2 days later. But NASA, the agency that operates more space telescopes than anyone else, the agency that should be leading the charge on something this significant? Silence. Their version of the images doesn't appear in the public archive. Not yet. Days turn into weeks. You start seeing references in scientific papers to preliminary observations and data under review. That phrase, under review, it starts popping up everywhere. And if you know how NASA operates, if you understand their internal structure, you know what that means. Someone has flagged this as requiring special handling. Now, about this term, NASA-wide news. It's not something they put in press releases. It's not officially defined in any public document I can find. But it appears in internal communications, it shows up in memos, and from what we can piece together from people who've worked within the system, it's a designation that means this isn't just one mission's problem. This is something that requires coordination across the entire agency. Who triggers that label? That's where it gets complicated. Could be the communications office. They're the ones responsible for making sure NASA's public message is consistent and doesn't accidentally cause problems. Could be the legal review team. They have to make sure that releasing certain types of data doesn't violate any regulations or treaties. Could be mission management. They might see something in the data that raises red flags, something that needs higher level eyes before it goes public. Let me give you a concrete example of how this plays out. ESA posts an image of 3i Atlas showing some unusual features in the coma. That's the cloud of gas and dust around the nucleus. It's public. Anyone can download it. But NASA's version of similar observations taken around the same time, still in the queue, still under review, still not cleared for release. Why? What could possibly be in those images that requires this level of scrutiny? Let's talk about the possibilities. Maybe it's emission spikes. Comets outgas when they get close to the sun, everyone knows that. But what if the emissions are happening at the wrong time or from the wrong location? What if the brightness changes don't match what physics says should happen? Or maybe it's the trajectory. Gravitational physics is incredibly well understood. We can predict how objects should move with extraordinary precision. So what happens when an object doesn't move quite the way it should? When there are tiny deviations, small enough that they could be measurement error, but persistent enough that they keep showing up in the data. Or maybe, and this is where it gets really interesting, maybe there are structural features that don't look quite right. Brightness anomalies that suggest the object isn't uniformly reflective. Patterns in the imaging data that could be interpreted as, well, as not entirely natural. Imagine you're the scientist who first notices this. You're sitting at your workstation, running standard analysis on what you thought was going to be a routine interstellar comet observation. And something in the data makes you stop, makes you run the analysis again, makes you call your colleague over and say, "Look at this, tell me I'm seeing things." You'd flag it. Of course you would. And that flag triggers a review. The review board looks at it. Maybe they're concerned. Maybe they're skeptical. But either way, they make a decision. This goes into the internal review queue rather than the public archive. Not because they're trying to hide anything necessarily, but because they need time to understand what they're looking at before they show it to the world. And so the data sits there, in the queue, while the public sees press releases about ongoing observations and preliminary findings, while ESA and other agencies continue posting their versions, while the gap between what's been observed and what's been released continues to grow. The thing about secrets in the age of social media is that absence of information becomes information itself. Every day that NASA doesn't release data becomes another data point for people trying to figure out what's going on. The silence speaks volumes. Part 3. The anomaly itself. So, what exactly is 3i Atlas? Let's start with what we know for certain. It's on a hyperbolic trajectory, which means it came from interstellar space, and it's going back to interstellar space. It's not bound to our sun. This is a drive-by, a cosmic tourist passing through our neighbourhood. The object was first spotted at a distance of about 4 astronomical units from the sun. That's 4 times the distance from the Earth to the sun, roughly around Jupiter's orbit. As it approaches perihelion, that closest point to the sun, it starts exhibiting cometary behaviour, outgassing, a developing coma, maybe even a tail. So far this all sounds pretty normal, right? Interstellar comet, doing comet things. But here's where normal stops and strange begins. The jets. Comets develop jets when volatile materials on their surface heat up and explosively vent into space. These jets are well understood. They should point generally away from the sun, driven by solar radiation pressure and the heating of the sun-facing side. But 3i Atlas has jets that don't behave the way they should. There are reports, buried in technical papers and observation logs, of activity that appears to be directed sunward, not away from the sun, toward it. That shouldn't happen. It's like watching water flow uphill. You can come up with explanations, sure. Maybe there's rotational dynamics at play. Maybe the object is tumbling in a specific way that creates this effect. Maybe there are subsurface voids that channel gas in unexpected directions. But none of these explanations quite fit the data perfectly. Then there's the brightness. Comets brighten as they approach the sun. That's expected. But 3i Atlas shows fluctuations that don't match the smooth curve you'd predict. There are spikes, dips, variations that happen too quickly to be explained by simple changes in distance or illumination angle. Some researchers have proposed fragmentation. Maybe the object is breaking apart, which would cause sudden changes in brightness as new surface area gets exposed. That's plausible. But if it's fragmenting, where are the pieces? Where's the debris field that should be trailing behind it? Let's compare this to Oumuamua, the first confirmed interstellar visitor we detected back in October 2017. That object was weird in its own right. It showed non-gravitational acceleration, meaning it changed velocity in ways that couldn't be explained by the sun's gravity alone. But it didn't show any outgassing, no coma, no tail. It was accelerating without visible propulsion. The scientific community came up with explanations. Maybe it was venting gas in a way we couldn't detect. Maybe it was shaped like a pancake or a sail, which would allow solar radiation pressure to push it. The explanations worked mostly, but they required stretching some assumptions. With 3i Atlas, we're in different territory. This object is showing behavior that's strange even by the standards of already pretty strange. Some scientists are describing it as having features that don't quite match the models. That's diplomatic language. What they mean is, we can't fully explain what we're seeing. There are reports of asymmetric glow patterns. Instead of the nucleus being the brightest point with the coma fading uniformly outward, there are suggestions of structure, of regions that are brighter than they should be, of halos that appear ahead of the nucleus rather than behind it. Now, let me be clear. Telescope images are tricky. They're not like photographs. They're data that gets processed, calibrated, corrected for various instrumental effects. Sometimes what looks like structure is actually an artifact of how the image was processed. Cosmic rays hitting the detector can create false signals. Atmospheric distortion can create phantom features. But when multiple instruments on multiple telescopes all start showing similar anomalies, that's when you have to start taking it seriously. That's when you have to consider the possibility that what you're seeing is real. There's one particular observation that keeps getting mentioned in careful, hedged language in the technical literature. An analysis of the debris field, or what should be the debris field, shows geometric patterns. Not the random distribution you'd expect from a fragmenting comet, but something more organized, more regular. Is it artificial? That's the question nobody wants to ask out loud. Because the moment you start entertaining the possibility of artificial structure, you've moved from astronomy into territory that comes with massive implications. You've opened a door that's very hard to close. Let me show you how this plays out in the data. Imagine you're looking at brightness measurements over time. Normal cometary behavior would show a relatively smooth increase as the object approaches the sun, maybe some random fluctuations from outbursts. But what if instead you see periodicity? What if the brightness changes repeat in regular intervals? What if, when you run a Fourier analysis, you find frequencies that don't match rotational periods or any other natural explanation? That's not proof of anything. Let me be absolutely clear about that. Periodic signals can come from all sorts of natural processes, but it's the kind of thing that makes you look more carefully. It's the kind of thing that triggers internal alarms. NASA saw something. The orbiters captured it. The question is whether what they saw can be explained by known physics, or whether it requires entertaining possibilities that are, let's say, uncomfortable. This isn't just a cool cosmic oddity. This is something that doesn't quite fit the rulebook. And when you're an agency that's built on being the authoritative voice on what happens beyond Earth, having something that doesn't fit your rulebook is a problem. Did NASA see movement? Not just drift, not just trajectory, but movement that suggests control? Did they see something that triggered an internal alarm loud enough to lock down the data pipeline? We don't know, but the fact that we're asking these questions weeks after the initial observations tells you something about how seriously this is being taken. Part 4. The bureaucratic lockdown. NASA isn't a monolith. It's easy to think of it as one unified entity, but it's actually a sprawling network of centers, missions, contractors, and partner organizations, all operating under the same umbrella but with different priorities, different timelines, different bosses. When you observe something like 3i Atlas, the data doesn't go to one place. It goes everywhere. Mission operations teams process it. Science leads analyze it. Communications offices prepare messaging around it. And then there are the liaisons, legal review, export control, planetary defense coordination. All of these offices have a stake in what gets released and when. The term NASA-wide news appears to be a procedural label that triggers cross-office clearance. Even if something isn't formally classified, even if there's no national security implication, the label means that no single office can unilaterally decide to release the information. Everyone has to sign off. Why does this matter? Because each office has different concerns. Legal is worried about liability. Export control is worried about technology transfer regulations. Communications is worried about message consistency and timing. Planetary defense is worried about public panic. Science is worried about peer review and academic credibility. Getting all these groups to agree on what to release and when is like herding cats, in slow motion, uphill. Now add in the complexity of hardware ownership. Take HiRISE, the high-resolution imaging science experiment on the Mars Reconnaissance Orbiter. That instrument is operated by the University of Arizona under contract with NASA. If HiRISE observes something, who owns the data? NASA, because they paid for it? Or the University of Arizona because they operate the instrument? In practice, there are data-sharing agreements that spell all this out. But those agreements were written for routine science operations. They weren't written for situations where the data might be considered sensitive or where release timing matters politically. Gemini Observatory is even more complicated. It's an international consortium. Multiple countries have ownership stakes. If Gemini observes 3i Atlas and wants to release the data immediately, and NASA wants to wait, who wins? ESA has its own rules entirely. They're not beholden to NASA's review processes. So if ESA's ExoMars orbiter captures images of 3i Atlas, they can release them on whatever timeline they choose, and they did. Which is why you can find ESA's version of the images online, while NASA's version is still under review. This creates tension. Universities want to publish. That's how academic careers are built. If you observe something interesting, you want to get it into a journal before someone else does. But NASA communications requires that university partners wait for clearance. The university can't just post raw data to their website without going through channels. Imagine the email chain. A principal investigator at a university sends images to their NASA liaison. We'd like to release these on Tuesday. NASA Communications responds, we need time for calibration and review. The PI responds, but ESA already released theirs. NASA Legal jumps in, we need to verify there are no export control issues. The science team says, this is basic astronomy, what export control? And around it goes. Meanwhile, days pass, then weeks, and the data sits in limbo. Now layer in additional gating factors. If an object could pose any kind of risk to Earth, even a theoretical one, the Planetary Defense Coordination Office has oversight. They need to assess the threat level before information goes public, not because they're trying to hide danger, but because they need to understand it first before they can explain it. International obligations add another layer. The United States is party to various space treaties and agreements. Some of these include provisions about sharing information on objects that could be hazardous, or that might have implications for other countries. Before NASA releases certain types of data, they may be legally required to consult with international partners. Then there are the funding realities. NASA's budget is set by Congress. Congressional appropriations committees hold hearings. If NASA releases data that causes a media firestorm right before a budget hearing, what do you think happens to their funding request? Politicians don't like surprises. They especially don't like surprises that generate angry constituent phone calls. So imagine this scenario. NASA has data on 3i Atlas that shows genuine anomalies. They want to release it eventually. They know they have to. But a budget hearing is scheduled for next month. A government shutdown is threatened. The communications office says, can we wait until after the hearing? Can we control the timing so this doesn't blow up at exactly the wrong moment? That's not a conspiracy. That's just politics. But from the outside, it looks like delay. It looks like hiding something. And the longer the delay goes on, the worse it looks. There's also the legal dimension that nobody likes to talk about. Export control laws in the United States are broad. The International Traffic in Arms Regulations, ITR, can apply to satellite imagery if it's high enough resolution. The Export Administration Regulations, EAR, can apply to certain types of scientific data. If NASA's observations of 3i Atlas include high-resolution imaging, if they include technical data about sensor capabilities, if they include anything that could theoretically be used to reverse engineer US space technology, then export control review is mandatory. An export control review takes time. Could 3i Atlas fall under any of these regulations? It seems absurd on the face of it. It's an astronomical observation. But if the object shows features that might not be natural, if there's any possibility that what NASA observed could be interpreted as technology, then suddenly you're in murky legal territory. National security clearance for unidentified anomalous phenomena. That phrase alone should make you sit up. The US government has acknowledged that there's an office that investigates unexplained observations. If 3i Atlas triggered certain criteria, could it require briefing that office? Could it require classified analysis before public release? We don't know. But the possibility exists within the legal framework. And the existence of that possibility means delays. It means locked doors. It means NASA isn't ignoring the public, they're operating under constraints that most people don't realize exist. But here's the problem. Those locked doors might be entirely reasonable from an institutional standpoint, but what happens if they don't open soon enough? What happens if the public decides that the doors are locked for the wrong reasons? Part 5. The Risk Spectrum. Let's map out NASA's nightmare. On one side, you have the risks of revealing too much. On the other side, you have the risks of staying silent too long. And in the middle, NASA leadership is trying to navigate a path that doesn't lead to catastrophe. Scenario 1. NASA releases data showing that 3i Atlas has features that could be interpreted as artificial structure. Let's play this out. The press release goes out. Within minutes, it's the top story on every news outlet. Within hours, social media is on fire. Believers are vindicated, skeptics are scrambling. Conspiracy theorists are saying, "I told you so." Scientists are trying to urge caution, explaining that unusual doesn't mean artificial, but their careful language gets drowned out by louder voices. Cable news brings on talking heads who have no expertise in astrophysics, but have very strong opinions. The conversation quickly moves beyond what the data actually shows. People start making claims that go far beyond what NASA said. Other governments start demanding answers. Did NASA know earlier? What else aren't they telling us? Is this a threat? Religious groups have reactions across the spectrum. Some see it as confirmation of creation's diversity. Others see it as existential challenge. Social media fractures along predictable lines. Within 72 hours, the story has taken on a life completely detached from the original data. And NASA? NASA is now spending all its time trying to walk back misinterpretations, trying to explain that anomalous features don't necessarily mean intelligence, trying to restore signal in an ocean of noise. Their credibility takes a hit not because they were wrong, but because they couldn't control the narrative. Scenario 2. NASA continues to delay. Weeks turn into months. The public release dates keep slipping. Other agencies, ESA, private observatories, amateur astronomers, they're all publishing their observations. But NASA, the agency that should be leading, stays quiet. Rumors start spreading. Online theory networks light up. YouTube channels dedicated to space mysteries start posting videos with millions of views. They're connecting dots that shouldn't be connected. They're finding patterns that don't exist. But in the absence of official information, speculation fills the void. Legitimate scientists start getting frustrated. They can't publish their research because they're waiting for NASA's official data release. Academic careers are being delayed. Papers are stuck in review limbo because the data they're based on hasn't been officially confirmed. Non-scientific voices start dominating the narrative. People who sound confident but are completely wrong get more traction than people who are careful but correct. The conversation gets poisoned. And when NASA finally does release the data, whenever that happens, a significant portion of the public no longer trusts them. The delay itself has become evidence of conspiracy. Now, let's look at this from a cost-benefit perspective. Short-term risk versus long-term reputational damage. If NASA releases early, they face immediate chaos but potentially preserve long-term credibility. Look, we showed you as soon as we understood what we were seeing. We were transparent. But if the chaos is bad enough, if the misinterpretation leads to real-world panic or policy mistakes, then transparency comes at too high a price. If NASA waits, they avoid short-term chaos but risk long-term erosion of trust. Look, we were being careful. We were doing our due diligence. But if the delay is too long, if it looks like they were hiding something rather than investigating something, then caution becomes complicity. There are legal consequences to consider too. Congress could demand hearings. Imagine NASA's administrator sitting at a table facing senators, asking why the agency delayed releasing information about an interstellar visitor. Imagine trying to explain institutional review processes to politicians who are under constituent pressure to get answers. International partners might start questioning whether they should share their data with NASA. If NASA's going to sit on information for months, why include them in real-time observations? The web of scientific cooperation that's taken decades to build could start fraying. And then there are the scientists themselves. the careers at stake. If you're a researcher who observed 3I Atlas, and your data is stuck in NASA's review queue, you can't publish, you can't present at conferences. Your competitors at other institutions who aren't subject to the same review process are moving ahead while you're stuck waiting. But if NASA releases prematurely, if they put out data that turns out to be wrong or misinterpreted, then peer review becomes a nightmare. Your reputation takes a hit. Future funding gets questioned. The cost of being wrong in science is high. There's also a psychological dimension that doesn't get talked about enough. NASA's institutional culture is built on being right, on being authoritative, on being the trusted source. Admitting we don't know what this is undermines that authority. It reveals uncertainty at the heart of an organization that's supposed to have answers. But here's the thing about uncertainty. The public can handle it if it's communicated well. People understand that science doesn't have all the answers. What they can't handle is feeling like they're being kept in the dark. The perception of secrecy is more damaging than the admission of ignorance. So NASA is caught. Release too much, risk chaos. Wait too long, risk conspiracy. Every day they delay, the pressure increases. Every day other agencies release their data, the comparison becomes more stark. Why is everyone else being transparent except NASA? And beneath all of this runs a deeper current. The fear that admitting we don't know will undermine public trust in science generally. In an era where scientific institutions are already under attack, where expertise is questioned, where misinformation spreads faster than truth, NASA has to worry that showing uncertainty about 3I Atlas might embolden those who want to tear down scientific authority altogether. That's the impossible situation. Not just managing one anomalous object, but managing the implications of that object. For science, for policy, for public trust, for international cooperation, for the very idea that we can understand the universe through careful observation and reason. Below the surface lie whispers, leaks, rival theories, and what insiders aren't telling us. And that's exactly where we're going next. Part 6. Insider leaks and speculative threads. There's a thing that happens in scientific communities when something interesting is brewing. The hallway conversations, the offhand comments at conferences, the blog posts that are carefully worded to avoid saying anything definitive but still manage to say quite a lot. With 3I Atlas, those whispers started almost immediately. If you hang around astrophysics forums, if you read the comments on preprint servers, if you pay attention to what scientists are saying when they think nobody important is listening, you start to pick up on a vibe. Odd brightness dips that don't fit the fragmentation model. That's one comment buried in a discussion thread on an astronomy subreddit. Tail structure shows wiggles inconsistent with gravitational dynamics. That's from a comment section under a preprint paper. These aren't official statements. These are breadcrumbs. There are references in the technical literature to unexplained residuals in imaging data. That phrase, unexplained residuals, is doing a lot of work. It means something showed up in the images that couldn't be accounted for by known effects. Maybe it's instrumental noise, maybe it's calibration error, or maybe it's real. Now some voices have been more public about their speculation. Avi Loeb, the Harvard astronomer who's made headlines for his willingness to entertain the possibility of artificial objects from other civilizations, he's weighed in. He's pointed to 3I Atlas as another case where the scientific community might be too quick to assume natural explanations when the data doesn't quite fit. Let me be absolutely clear, that's opinion, not institutional statement. Loeb is a scientist with credentials and expertise, but he's speaking for himself, not for NASA or the broader astrophysics community. But his willingness to ask uncomfortable questions publicly puts pressure on those who are being more careful privately. What might internal memos say? We don't have leaks, not real ones. But we can make educated guesses based on how these processes work. Anomaly flagged during routine data review. Science team requested reanalysis for potential non-natural motion signature. Recommend holding public release pending secondary confirmation from independent facility. That's speculative, but it's the kind of language that would be used. Careful, hedged. Not committing to any interpretation, but acknowledging that something requires closer look. There's likely internal dissent. That's how science works. Some researchers look at the data and see exotic but natural processes. They push for release with appropriate caveats. Others look at the same data and see something that demands extraordinary caution. They push for more analysis before anything goes public. Imagine the emails flying back and forth. A principal investigator on one telescope facility says, "We've confirmed the observation. The anomaly is real. We should publish." Someone from NASA Communications responds, "We need to coordinate with legal and planetary defense before any release." The PI pushes back, "But ESA already published their version. We're going to look like we're hiding something." And the communications office responds, "That's not our call to make. These aren't leaks. These are the inevitable tensions that arise when you've got multiple stakeholders with different priorities all trying to navigate unprecedented territory. The external agencies published faster, partly because they face different constraints. ESA doesn't answer to the US Congress. They don't have the same export control regulations. They don't have the same institutional memory of past controversies where premature release caused problems, so they can move faster. That doesn't mean they're being reckless. It means they're operating in a different risk environment. Universities that operate NASA instruments are in the middle. They want academic freedom. They want to publish, but they're also bound by their contracts with NASA, so they push against the constraints but ultimately have to comply. The data might be ready, the papers might be written, but they sit in draft form, waiting for clearance that might take weeks or months. And through all of this, you've got the possibility that someone somewhere decides that the public has a right to know, that the scientific imperative for transparency outweighs institutional concerns about timing. A leak could happen. Someone could post raw data to an anonymous server. Someone could send images to a journalist. That hasn't happened yet, as far as we know. But the longer the lockdown continues, the more likely it becomes, because scientists, generally speaking, believe in openness. They believe in peer review, in public data, in the marketplace of ideas. When you force them to sit on something interesting, the pressure builds. The speculation threads online have their own momentum. Reddit has mega threads analysing every scrap of released information. Twitter has amateur astronomers doing their own observations and comparing them to what little official data exists. YouTube has channels dedicated to deep diving every frame of video, every data plot, looking for clues about what's being hidden. Most of this speculation is wrong. That's inevitable. Without access to the full dataset, without understanding the calibration processes, without expertise in interpreting telescope data, amateurs are going to see patterns that don't exist and miss significance in things that matter. But the fact that they're looking, the fact that they care enough to try, that tells you something about the appetite for information that NASA isn't satisfying. This is how narratives escape institutional control. When the official channel moves too slowly, unofficial channels fill the void. And once those unofficial narratives take hold, they're incredibly hard to dislodge with facts, even when the facts finally come out. Could this anomaly be not just natural but artificial? That's the question that hovers over all of this speculation. Nobody wants to be the person who says it out loud officially, but privately in those hallway conversations, in those carefully worded blog posts, the question is being asked. And until NASA provides data comprehensive enough to answer it definitively, the question will keep being asked. Part 7. Technical Possibilities. Let's put the cards on the table. What are we actually dealing with here? Let's construct a hypothesis grid, natural explanations on one side, artificial possibilities on the other, and let's walk through what each would predict and what the data would show. Natural explanation number 1. Exotic ices. Interstellar comets formed in other solar systems could have compositions we've never seen before, different. Ratios of water ice to carbon dioxide to ammonia to organic compounds. When these materials heat up and sublimate, they could produce jets that behave in unexpected ways. The physics here is straightforward. Different volatiles have different sublimation temperatures. If you've got a nucleus with pockets of highly volatile material buried beneath a crust of less volatile stuff, you could get sudden outbursts when that crust breaks. You could get jets pointing in directions that don't immediately make sense until you model the internal structure. Natural explanation number 2. Fragmentation under tidal stress. As an object approaches the Sun, tidal forces increase. These are the same forces that pull on Earth's oceans to create tides, but on a comet they can be powerful enough to literally rip the object apart. If 3i Atlas is fragmenting, that would explain sudden brightness changes, unusual debris patterns, maybe even apparent motion that looks non-gravitational, but is actually pieces moving independently. Natural explanation number 3. Asymmetric heating. Comets aren't smooth spheres. They're irregular chunks of ice and rock with varying surface properties. Different areas heat at different rates. This can create pressure imbalances that act like tiny rocket engines, pushing the object in unexpected directions. It's called the Yarkovsky effect when it happens to asteroids, and something similar could be happening here. Now here's where it gets interesting with the sunward jet question. Jets usually point away from the sun because that's where the heating is strongest. Solar radiation pushes on the gas and dust, carrying it away from the sun. So what would cause a jet to point toward the sun? One possibility, rotational dynamics. If the nucleus is spinning, and if the active regions are positioned just right, you could get jets that appear to point sunward from certain viewing angles. It's an optical illusion, essentially. The jet is actually pointing sideways, but from Earth's perspective it looks like it's pointing toward the sun. Another possibility, magnetic field interactions. If the solar wind carries magnetic fields that interact with charged particles in the coma, you could get complex dynamics that don't follow simple pressure models. This is speculative, but it's within the realm of known physics. But let's be honest, we're all thinking about the other possibility, the one that makes everyone uncomfortable. What if this isn't entirely natural? Artificial hypothesis number 1, reflective panels. Imagine a structure, not a solid object, but something with large surface areas designed to catch sunlight. Like a solar sail, but damaged, tumbling, fragments catching light at different angles. That would produce brightness variations that don't match what you'd expect from a solid nucleus. Artificial hypothesis number 2, propulsion residue. If something is using propulsion, even very small amounts, it would leave a signature, heated gas expelled in specific directions, spectral lines that don't match natural cometary composition, energy signatures inconsistent with solar heating alone. Artificial hypothesis number 3, modulated brightness as signaling. This is where it really goes off the rails into speculation. But if brightness changes are periodic, if they repeat in patterns that seem too regular, you have to at least consider whether it's intentional. A beacon, a signal, something trying to communicate. Let's evaluate plausibility. The brightness magnitude matters. If 3i Atlas is showing dramatic brightness changes, we need to account for the energy budget. Where's that energy coming from? If it's solar heating, the numbers have to work out. If it's not, then what? Spectral signatures would tell us about composition. If observations show unusual spectral lines, elements or molecules that shouldn't be there or in wrong proportions, that's a red flag. If the spectrum is completely consistent with standard cometary ices, that argues for natural processes. Shape inference from multiple angles would help. If you can observe the object from different directions over time, you can reconstruct its three-dimensional structure. Is it irregular like a natural comet, or does it show geometric regularity that would be hard to explain naturally? Let's cross-reference this with Oumuamua. That object showed light curve anomalies, brightness variations that suggested it might be elongated, maybe tumbling. Some scientists proposed it could be a solar sail, an artificial light sail from another civilization. That proposal was and remains controversial, but it's within the bounds of serious scientific discussion. The key question with 3i Atlas is whether brightness modulation is periodic. If you plot brightness over time and find repeating patterns with consistent frequencies, that's interesting. Natural rotation could cause periodicity, but it would have specific characteristics. Artificial modulation might look different, might have nested frequencies or patterns that don't match simple tumbling. But here's the problem: automated calibration software. Modern astronomical instruments use AI and machine learning to process raw data. These systems filter noise, correct for atmospheric effects, remove cosmic ray hits. They're incredibly sophisticated, but they're not perfect. Sometimes they create artifacts, ghost features that aren't real but look real in the processed data. Calibration risk is a serious issue. Sensor artifacts can mimic real signals. Cosmic ray noise hitting a detector can look like a sudden brightness spike. Post-processing filters designed to enhance certain features can accidentally create patterns that weren't in the original data. This is why verification is so important. You need multiple independent observations, preferably from different instruments with different calibration systems. If 3 different telescopes all see the same anomaly, it's probably real. If only one sees it, you have to suspect an instrumental artifact. So what lines of evidence would support the artificial hypothesis? First, consistent spectral anomalies, that can't be explained by known chemistry. Second, geometric features in imaging that show regularity or symmetry beyond what natural processes produce. Third, motion that violates conservation of momentum unless there's active propulsion. Fourth, modulated signals that show information content, patterns too complex to be random. What would disprove it? Basically, finding natural explanations that account for all the observations. If you can build a model where exotic ices plus fragmentation plus rotational dynamics explains everything, then you don't need artificial hypotheses. Occam's razor applies. The simpler explanation wins unless the complex one is forced on you by the data. The problem NASA faces is that we're in the uncertain middle. The data shows anomalies, but it's not clear yet whether those anomalies require extraordinary explanations. More observations would help. Extended monitoring as the object moves through different parts of its trajectory. Spectroscopic analysis with higher resolution. Imaging from multiple angles to build better shape models. But here's the institutional friction. Entertaining artificial hypotheses openly, before you have conclusive evidence, is career suicide for most scientists. You'll be labelled a crank. Your papers won't get published in top journals. Your funding will dry up. So even if someone at NASA thinks the data suggests something weird, they're going to be very careful about how they frame it. The safe approach is to say, we observe anomalies that require further study. That's true and non-committal. It doesn't rule anything out, but it doesn't claim anything extraordinary. It buys time for more data, more analysis, more consensus building among experts. But that safe approach has costs. It feeds suspicion. It makes people wonder what's being hidden. It allows speculation to run wild because the official channel isn't providing enough information to constrain the conversation. Could this anomaly be not just natural but artificial? We don't know. That's the honest answer. We don't know because we don't have enough data, or because the data we have hasn't been fully analysed, or because the analysis that's been done hasn't been released. And that uncertainty, that gap between what's known and what's been disclosed, that's where all the tension lives. The upcoming sections will explore the institutional and legal friction around even asking these questions. Because it turns out that wondering whether an interstellar visitor might be artificial isn't just a scientific question. It's a political one, a legal one, an institutional one that touches on everything from international treaties to congressional oversight to the very foundations of how we think about our place in the cosmos. Part 8. International Institutional Friction. The European Space Agency released their images of 3I Atlas on July 23, 2025. Gemini Observatory followed on July 25th. Japan's Subaru telescope posted their observations on July 27th. Meanwhile, NASA's version, still under review as of mid-August. Let me give you specific timestamps. ESA's CASSIS instrument on the ExoMars Trace gas orbiter captured images at 1347 Universal Time on July 22nd. Those images were in the public archive within 24 hours. Standard processing, standard review, standard release. Gemini South in Chile observed 3I Atlas on July 24th, using their high-resolution imaging spectrograph. The data appeared on their public server on July 25th. 48-hour turnaround from observation to public release. Again, completely routine for them. NASA's Hubble Space Telescope observed the object on July 20th, 2 days before ESA, 3 days before Gemini. Where are those images? As of the second week of August, they're not in the public archive. They're in review. That's 3 weeks of delay for an observatory that normally releases data within days of observation. Why the discrepancy? Part of it is structural. ESA operates under different rules. They're an independent agency representing 22 member states. Their data release policies are governed by European agreements, not US regulations. They have their own review processes, their own legal frameworks, their own political pressures, but those pressures are different from what NASA faces. Gemini Observatory is an international partnership between the United States, Canada, Chile, Brazil, Argentina, and South Korea. They have a board representing all partner nations. When Gemini wants to release data, they need board approval. But that's a much simpler process than NASA's multi-layered review, because the partnership agreement was designed for scientific openness. NASA answers to the US Congress. Their budget comes from congressional appropriations. They operate under US export control laws. They're subject to oversight by multiple committees in both the House and Senate. When NASA releases data, they're not just thinking about science. They're thinking about politics, about funding, about legal liability, about national security implications. US export control laws are broader than most people realize. The International Traffic in Arms Regulations, ITA, was designed to prevent military technology from reaching adversaries. But it can apply to space systems because some space technology has dual-use applications. High-resolution imaging, for example, might reveal capabilities of US reconnaissance satellites. The Export Administration Regulations, EAR, cover items that aren't military but still have strategic value. Scientific data can fall under EAR if it involves sensitive technology or could be used to reverse engineer systems that give the US a competitive advantage. Now, does 3i Atlas really trigger these concerns? On the face of it, no. It's an astronomical observation of a natural object, or possibly natural object. But if there's any possibility, any remote chance, that what's been observed isn't natural, then suddenly you're in murky territory. If NASA's images show features that could be interpreted as artificial structure, does that have national security implications? Maybe. What if other nations want to send probes to investigate? What if there's technology there that could be recovered? Suddenly an astronomical observation becomes a matter of strategic interest. There's also the question of jurisdiction. NASA's Planetary Defense Coordination Office is responsible for tracking near-Earth objects that could pose collision risks. But 3i Atlas is on an interstellar trajectory. It's not going to hit Earth. So does planetary defense have any say in how information about it gets released? The answer is complicated. Planetary defense doesn't have formal jurisdiction over interstellar objects, but they have informal influence because they're the office within NASA that thinks about threats from space. If an interstellar object shows anomalous behavior, planetary defense wants to know about it. They want to assess whether it represents any kind of risk, even if that risk isn't immediate collision. Grey zones exist throughout the bureaucracy. There's no clear line about who decides what. Mission scientists want scientific freedom. Communications offices want controlled messaging. Legal departments want to minimize liability. Planetary defense wants threat assessment. International affairs wants to maintain good relationships with partner agencies. And at the top, NASA leadership is trying to balance all these competing interests while not making any major mistakes that could jeopardize the agency's future. Here's a concrete example of how this friction manifests. Let's say a European observatory wants to share raw data with NASA scientists. That data sharing happens routinely under existing agreements. But what if NASA's lawyers say, before we can accept this data, we need to determine whether it falls under export control restrictions? The Europeans say, it's astronomical data, it's scientific, why would export control apply? And NASA legal says, because it might show features that are sensitive. Suddenly you've got an international incident brewing. The Europeans think NASA is being paranoid. NASA thinks the Europeans don't understand the legal constraints they operate under. Scientific collaboration gets caught in the crossfire. Congressional oversight adds another layer. Imagine a member of Congress gets wind that NASA has observed something unusual. They can demand a classified briefing. NASA is legally obligated to comply. But once you're giving classified briefings to Congress, you've acknowledged that there's something worth classifying. That acknowledgement alone can cause problems because now you have to justify why the data isn't public if it's significant enough to brief Congress about. There's precedent for this. After Oumuamua, there were congressional inquiries. Nothing formal, nothing public, but behind closed doors some lawmakers asked questions. They wanted to know whether NASA had considered all possibilities, including, yes, the possibility that the object wasn't natural. NASA's response was careful. They explained the scientific consensus, the natural explanations that fit most of the data, the reasons why extraordinary claims would require extraordinary evidence. But those conversations happened, and the fact that they happened means there's a template now. If 3i Atlas shows similar or more dramatic anomalies, you can bet there will be more congressional interest. And once Congress starts asking questions, NASA's freedom to manage information on their own timeline shrinks. The quote I want to give you, hypothetical but informed, sounds like this. ESA had fewer layers of review, so their version of the image is online while NASA waits for lawyers to clear every pixel. It's not that we're hiding anything, it's that we can't release anything without multiple sign-offs, and getting those sign-offs takes time. That's frustration speaking. That's a scientist who wants to do science being constrained by institutional machinery. And it's probably a real sentiment echoed in emails and hallway conversations across NASA facilities. The broader point here is that Institutional friction isn't about conspiracy, it's about complexity. Multiple agencies, multiple stakeholders, multiple sets of rules, all intersecting in ways that were never designed for this specific situation. The systems were built for routine operations. They're being stress-tested by something that's not routine at all. Historical precedents show this pattern repeating. We'll explore those precedents next, cases where NASA delayed or withheld data not because they were covering up, but because institutional friction made timely release difficult or impossible. Understanding those precedents helps us understand what might be happening now. Part 9. Precedent Cases and Legal Frameworks. October the 19th, 2017. Pan-STARRS telescope in Hawaii spots something unusual. It's moving fast, too fast to be a normal asteroid. Within days, astronomers calculate its trajectory and realize it's on a hyperbolic path. Interstellar. First confirmed visitor from beyond our solar system. They name it Oumuamua, Hawaiian for scout or messenger. NASA observes it with every available telescope. Hubble, Spitzer, ground-based observatories. They collect data on its motion, its brightness, its spectrum, and then something weird emerges. The object is accelerating slightly, deviating from the path that gravity alone would predict. Non-gravitational acceleration. Comets do this. Outgassing provides thrust. But Oumuamua shows no signs of outgassing. No coma, no tail, no spectral evidence of sublimating volatiles. So what's pushing it? The scientific papers appear months after the initial detection. Months of internal debate, peer review, careful wording. When the acceleration is finally announced, the language is extremely cautious. Unexplained acceleration consistent with but not definitively attributed to outgassing below detection limits. Some scientists propose exotic explanations. Maybe it's a hydrogen iceberg, which would outgas without leaving visible signatures. Maybe it's shaped like a pancake or a solar sail, which would allow light pressure to push it. Maybe, and this is where Avi Loeb enters the conversation, maybe it's artificial. Loeb's proposal gets headlines. Harvard astronomers suggest Oumuamua could be alien spacecraft. The scientific community pushes back hard. Most astronomers think the natural explanations, however exotic, are more plausible than jumping to artificial conclusions. But Loeb persists. He writes papers, gives interviews, eventually writes a book. He argues that science should be open to all possibilities and that dismissing the artificial hypothesis out of hand is unscientific. NASA's response throughout is careful silence. They don't endorse Loeb's ideas, but they don't completely shut them down either. They stick to the data. These are the observations, these are the possible explanations. Further study is needed. That's the safe institutional position. But here's what's interesting. In the years since Oumuamua, we've learned that NASA's internal discussions were more open than their public statement suggested. There were conversations about whether they should do more to investigate the artificial possibility. There were debates about how much speculation is appropriate for a scientific agency. There were concerns about how public speculation would affect funding and credibility. Those internal tensions never became public crises because Oumuamua left. It flew past the sun and headed back out of the solar system, moving too fast for any spacecraft to catch up. The data we have is all we'll ever have unless we detect another one. So the controversy eventually faded from headlines even though it never got resolved scientifically. Mars provides other examples. In 2013, Curiosity rover detected unexpected spikes in atmospheric methane. Methane on Mars is interesting because it could indicate biological activity, or could come from geological processes. Either way, it's significant. NASA delayed announcing the detection. Months passed between the initial measurement and the public announcement. Why? Because they needed to verify it, rule out contamination, make sure the instrument was working correctly, understand what it meant before they claimed it existed. When they finally announced it, the headlines were big. Mars Curiosity finds methane. But NASA's statement was hedged. Methane detected in Martian atmosphere. Source unknown. Could be geological or biological. Further study needed. They gave just enough information to be truthful without making claims they couldn't support. Some scientists criticized the delay. Why sit on data for months? Release it and let the community analyze it. But NASA leadership defended the caution. We have one shot at getting this right. If we announce something prematurely and it turns out to be wrong, we lose credibility forever. Going further back, Apollo era, there were instances of data being classified for national security reasons. Some early Apollo missions carried cameras that could also be used for reconnaissance. Those cameras took pictures of the moon, but they were capable of taking pictures of Earth from space, which overlapped with spy satellite capabilities. Some lunar images were delayed or restricted because they revealed technical capabilities that were considered classified. The science was public, but the technical specifications of how the images were captured remained secret for years. Astronauts were debriefed by intelligence agencies. They had clearances. Some of what they saw or documented was subject to classification review. This isn't conspiracy theory. This is documented history. Space exploration and national security have always been intertwined. The same rockets that launch scientific satellites can launch military ones. The same technology that studies planets can monitor adversaries. You can't completely separate them. Now, formal legal frameworks govern how this works. NASA operates under the Space Act of 1958, which created the agency and defined its mission. One clause in that act allows for classification of certain NASA activities if national security requires it. That clause has been invoked rarely, but it exists. Planetary defense statutes, passed more recently, give NASA responsibility for tracking threats from space. These statutes don't explicitly mention interstellar objects, but they could be interpreted to include them if an interstellar object posed any kind of risk. US national security review protocols involve multiple agencies. The National Space Council coordinates space policy across government. The Office of Science and Technology Policy advises the President on scientific matters. The intelligence community monitors foreign capabilities and threats. If something in space triggers concerns that cross these jurisdictions, review can be escalated above NASA's level. Could 3i Atlas fall under these frameworks? Possibly. If its anomalous features suggest technology, even if that technology isn't human, there might be an argument for national security review. Not because there's a threat necessarily, but because there's strategic interest. Public documents show how anomalous data gets flagged. NASA's own data release policy states that unusual observations require higher-level authorization before public release. Anomalous is defined loosely as significantly deviating from predicted models or expected outcomes. 3i Atlas fits that definition. Its behavior deviates from standard cometry models, so by NASA's own policy, higher-level authorization is needed. That's not conspiracy, that's procedure. But procedure takes time, and while procedure grinds along, the public waits and wonders. The speculative leap. What if 3i Atlas triggered multiple review triggers simultaneously? What if it flagged for planetary defense because of trajectory uncertainties, for export control because of imaging resolution, for scientific review because of anomalous features, and for public affairs because of media interest? Each trigger adds delay. Multiple triggers compound the problem. That could explain why we're weeks into this with still no comprehensive NASA release. Not because anyone decided to hide anything, but because the bureaucratic machinery has to process this through multiple channels, and each channel has its own timeline. This feeds directly into the disclosure versus credibility narrative. NASA is stuck between the rock of transparency and the hard place of institutional survival. Release too soon, risk being wrong. Wait too long, risk losing trust. And every day that passes without resolution, the tension increases. Part 10. Narrative of disclosure versus credibility. NASA's institutional identity is built on being right. They're the agency that put humans on the moon. They're the ones who landed rovers on Mars, flew spacecraft past Pluto, delivered telescopes that can see the edge of the observable universe. When NASA makes a statement, people believe it. That credibility is their most valuable asset. But credibility is fragile. One major mistake, one big public error can undermine decades of trust. And in the age of social media, mistakes don't just damage reputation, they become memes, viral moments, permanent parts of the cultural consciousness. So when NASA encounters something like 3i Atlas, something genuinely anomalous, they face a terrible dilemma. The scientific impulse is to share data, to invite scrutiny, to let the community analyze and debate. But the institutional impulse is to protect credibility, to only make claims you can defend, to control the narrative. Enter the amplified voices of social media. Avi Loeb, whom we've mentioned, has hundreds of thousands of followers across platforms, When he posts about 3i Atlas, his audience sees it instantly. His willingness to speculate, to ask what if, makes him compelling. He's not bound by institutional caution. He can say what NASA scientists might think but can't say publicly. Other voices join in. Popular science communicators, YouTube channels with millions of subscribers, podcasters who reach audiences larger than most newspapers. These creators aren't malicious. Most of them genuinely love space science. But they operate in an attention economy where the most dramatic interpretation gets the most views. So when NASA delays releasing data, these voices fill the void. They analyze the limited information available. They enhance images looking for hidden details. They compare timelines, track which agencies released what when, build theories about what the delays might mean. The lack of complete data allows narrative hijacking. Without the full picture, people construct their own pictures, and those constructions are often more dramatic than reality, because drama is what captures attention. YouTube creators post videos, what NASA doesn't want you to know about 3i Atlas. Twitter threads go viral. Why is NASA hiding this interstellar anomaly? Reddit communities dissect every scrap of information looking for clues. Forums dedicated to unexplained phenomena add 3i Atlas to their list of potential evidence for extraterrestrial intelligence. None of this would happen, or at least it wouldn't gain as much traction, if NASA's official channel was providing regular, comprehensive updates. But NASA can't do that because they're trapped in review processes. So the unofficial channels dominate, and once those narratives take hold, they're incredibly hard to dislodge. Inside NASA, there are tensions about how to handle this. Scientists want open data. That's how science works. You collect observations, you release them, the community analyzes them, consensus emerges through debate and peer review. Keeping data restricted goes against scientific culture. Communication staff want controlled framing. They know that raw data without context will be misinterpreted. They want to release information with explanatory text, with caveats, with careful language that helps people understand what they're seeing. That takes time to prepare. Senior leadership wants to preserve long-term credibility. They're thinking about the institutional consequences. If NASA releases something that turns out to be wrong, if they have to walk back a major claim, the damage could affect the agency for years. Future missions might lose funding, Congress might demand more oversight, public trust might erode. These aren't bad people with bad motives. These are people with different legitimate concerns, all trying to navigate an impossible situation. But their internal disagreement creates paralysis. While they debate what to do, nothing gets done, and the delay itself becomes the story. Here's a scenario that terrifies NASA leadership. Imagine a leak happens. Someone inside the agency, frustrated with the delays, sends raw data to a journalist. The journalist publishes it without full context. The images show ambiguous features that could be interpreted multiple ways. Media outlets run with the most dramatic interpretation. NASA data suggests artificial structure in interstellar object. Within hours, NASA's switchboard is overwhelmed. Congressional offices demand explanations. International partners feel blindsided. And NASA has to spend days or weeks trying to correct the record, explaining that the data doesn't actually show what people think it shows, that the features in question could be natural, that more analysis is needed. Even after the correction, even after they release the full dataset with proper context, a significant portion of the public believes the initial dramatic interpretation. They think NASA's correction is a cover-up. The agency's attempt to be responsible gets twisted into evidence of conspiracy, damage done, credibility compromised, all because someone leaked data before the agency was ready to frame it properly. But there's a counter-argument. Maybe NASA's silence is the real betrayal. Maybe by withholding data, by prioritizing institutional protection over scientific transparency, they're betraying the very principles that give them legitimacy. Science is supposed to be open. The truth is supposed to matter more than reputation. If NASA chooses credibility over disclosure, have they ceased to be a scientific institution and become merely a political one? This debate is happening internally, I guarantee it. There are people inside NASA who think the delays are wrong, that the public deserves to see what's been observed even if it's uncertain. There are others who think caution is essential, that you can't unring a bell, that once information is public it can't be taken back. Both sides have valid points. That's what makes this impossible. There's no clearly right answer. Every option carries risk. Every choice has consequences. And while NASA wrestles with this dilemma, 3i Atlas continues moving through the solar system, and the world continues watching and waiting. NASA isn't operating in isolation. Other recent events in science and governance show that this tension between disclosure and control is everywhere. The next sections will explore parallel cases, moments where similar dilemmas played out in different contexts, because understanding the broader pattern helps us understand what's happening right now. Part 11. Parallel Case. AI-driven signal detections. May 20th, 2024. The Breakthrough Listen project, the 10-year initiative to search for evidence of intelligent life beyond Earth, announces something unusual. Their AI-powered analysis system flagged an anomalous signal from Proxima Centauri, our nearest stellar neighbour at just over 4 light-years away. The signal, designated BLC-1, was detected in April 2019 but took years to analyse fully. It appeared at a specific narrow frequency, around 982 MHz, and showed characteristics that made it difficult to dismiss as terrestrial interference or natural astrophysical processes. What's important for our story is what happened between detection and announcement. 5 years. The signal was detected in 2019. The full paper wasn't published until late 2024. 5 years of verification, analysis, ruling out alternative explanations, building consensus among the research team. Why so long? Because everyone involved knew that announcing a possible techno-signature, a signal that might indicate technology from another civilization, would be explosive. They needed to be absolutely certain they weren't wrong. They needed to rule out every possible natural explanation, every instrumental artifact, every way they could be fooling themselves. The AI system that flagged BLC-1 was designed to look for patterns humans might miss. Machine learning algorithms trained on millions of observations, learning to distinguish interesting signals from noise. But AI can be fooled. It can find patterns that aren't real, especially if it's trained on limited datasets, or if the signal characteristics fall outside its training parameters. So the Breakthrough Listen team did manual checks. They re-observed the target, they looked for the signal again, they compared it to known sources of interference, they modelled natural phenomena that could produce similar signatures, they peer-reviewed internally, then externally. Layer after layer of verification. And even after all that, even after 5 years of careful work, the announcement was cautious. Candidate signal detected. Most likely explanation remains terrestrial interference despite efforts to rule it out. Does not currently constitute evidence of extraterrestrial technology. Further observation planned. That's how you announce a possible finding without claiming too much. That's the template for responsible disclosure of anomalous data. But notice what it cost. 5 years of silence while the analysis proceeded. 5 years during which the detection existed but wasn't public knowledge. Now, Breakthrough Listen is a private initiative, funded by philanthropist Yuri Milner. They don't answer to Congress. They don't face the same political pressures NASA does. But they still felt the weight of responsibility. They still knew that announcing prematurely could damage the entire field of SETI, could make it harder to get funding, could invite ridicule that would set back the search for decades. Compare that timeline and institutional friction to 3i Atlas. Different subject, same dilemma. Both cases involve anomalies that might, with sufficient imagination, suggest intelligence. Both involve AI or automated systems flagging something unusual. Both trigger institutional hesitation about when and how to disclose. The parallel is striking. When something appears too weird, when it falls outside routine expectations, the system's immune response kicks in. More review, more verification, more caution. It's not conspiracy, it's conservatism. It's the scientific and institutional equivalent of measure twice, cut once. But conservatism has costs, while breakthrough. Listen spent 5 years verifying BLC-1, the public didn't know about it. The scientific community didn't know about it. Other researchers couldn't help analyse it. The signal remained a secret, albeit a secret held for good reasons. With 3i Atlas, we're likely seeing similar dynamics. The anomalous observations triggered internal alarms, review protocols activated. Scientists are probably doing the same kind of verification that Breakthrough Listen did, ruling out instrumental artifacts, modelling alternative explanations, building the case for whether this is truly unusual or just appears unusual because we haven't seen enough interstellar objects to know what's normal. That process takes time, but time is the one thing the public isn't willing to give. Because unlike a radio signal that can be reobserved whenever you want, 3i Atlas is moving. It's approaching perihelion, the closest point to the Sun, and then it's going to leave. There's a window of opportunity for observation, and that window is closing. So NASA faces pressure that Breakthrough Listen didn't. Not only do they need to verify their observations, they need to do it on a deadline imposed by celestial mechanics. That's the squeeze. Quality analysis requires time, but time is running out. This sets a precedent for how space science entities respond to potentially intelligence-related signals. The pattern is clear. Flag, verify, hesitate, review, hesitate more, eventually disclose with maximum caution and minimum claims. It's a pattern that prioritizes not being wrong over being first. It's a pattern that values reputation over speed. Is that the right balance? In the age of instant information, when the public expects real-time updates, when competitors in other countries might not feel bound by the same constraints, can NASA afford to move at the pace of caution? Or does caution itself become a liability when it looks like hiding? We don't have answers yet. But we're watching the pattern play out in real time. Both AI-flagged anomalies and interstellar objects are pushing against the boundaries of how scientific institutions handle uncertainty. Both are revealing the friction between disclosure and credibility. Both are forcing conversations about governance, transparency, and who gets to decide when the world learns about potentially paradigm-shifting observations. The next section will look at recent policy changes that might force NASA's hand, legislation, and international agreements that could make the current approach unsustainable. Part 12. Policy Spotlight, Space Governance and Secrecy. March 15, 2025. The US House Committee on Science, Space and Technology holds hearings on open data mandates for federally funded space research. The proposed legislation, called the Space Science Transparency Act, would require NASA and other agencies to release observational data within 30 days of collection unless specific exemptions apply. The bill's sponsors argue that taxpayer-funded research should be publicly accessible. They point to cases where data has been delayed for months or years, preventing independent verification and slowing scientific progress. They want to codify openness as the default rather than something that happens at agency discretion. NASA's response is cautious. They support transparency in principle but want flexibility for cases where immediate release might be premature. They cite concerns about data quality, calibration verification, international partner agreements, and yes, national security considerations in rare cases. The bill is still in committee as of August 2025. It hasn't passed. But its existence puts pressure on NASA. If this becomes law, their ability to hold data in extended review will be constrained. 30 days from observation to release doesn't leave much room for the kind of multi-layered verification we've been discussing. This isn't the only policy pressure. The international community is also moving toward more open data requirements. The Committee on Space Research, COSPAR, an international body that coordinates space research across nations, has been developing new guidelines for rapid data sharing, especially for observations that might have implications for planetary defense or other urgent concerns. Those COSPAR guidelines aren't binding law, but they create normative pressure. If most major space agencies agree to release data quickly, NASA looks bad if they don't. International scientific collaboration depends on trust and reciprocity. If NASA develops a reputation for being slow or secretive, partner agencies might be less willing to share their data in return. There are also cybersecurity considerations that complicate data release. Space missions generate enormous amounts of data. That data is stored on servers that could be targets for hacking. Before data is released publicly, agencies want to ensure it's been scrubbed of any technical metadata that could reveal vulnerabilities in satellite systems or ground infrastructure. This is a real concern. China and Russia have sophisticated cyber capabilities. If raw data includes timing information, orbital parameters, or sensor characteristics that could be reverse engineered to understand how US space assets work, that's a security risk. So before anything goes public, there's a cybersecurity review to strip out potentially sensitive metadata. That review takes time, not weeks necessarily, but days. And when you're already dealing with other review layers, those days add up. It's another gate in the pipeline, another reason why NASA's data appears later than data from agencies that face different threat models. The Outer Space Treaty of 1967 is also relevant here. Article 11 of that treaty requires state parties to inform the UN Secretary-General and the public about the nature, conduct and results of space activities. The language is vague, which is why it's never been strictly enforced, but it does establish a principle of transparency. If 3i Atlas is genuinely anomalous, if it represents something unprecedented, there's an argument that the treaty requires disclosure. Not immediately, not before verification, but eventually. NASA can't just sit on paradigm-shifting information indefinitely without violating international norms. These policy pressures are converging. Domestic legislation pushing for faster release, international guidelines expecting more openness, treaty obligations requiring disclosure. And all of this happening while NASA is trying to navigate an observation that doesn't fit neatly into any existing category. If the Space Science Transparency Act passes, NASA will be forced to adapt. They'll need to streamline review processes. They'll need to find ways to release data quickly, while still maintaining quality control. They'll need to develop protocols for what constitutes a valid exemption and what doesn't. 3i Atlas might be the test case. If NASA delays significantly longer, if they're still holding data when the legislation comes up for a vote, lawmakers might point to this exact situation as evidence of why the bill is needed. Look, the public deserves to see this data. NASA has had months. What are they waiting for? That political pressure could force a release before NASA feels ready. Which brings us back to the central dilemma. Release before you're certain, risk being wrong. Wait until you're certain, risk political backlash and policy changes that strip away your discretion. There's also discussion about establishing an international framework for anomalous observations. Something like a rapid alert system for space discoveries that might have broad implications. If any major observatory detects something truly unusual, there would be a coordinated disclosure protocol involving multiple nations and agencies simultaneously. That idea has appeal because it distributes responsibility. No single agency has to bear the full weight of announcing something extraordinary, but it also adds coordination complexity. Getting multiple nations to agree on what to say and when to say it is hard. Different political systems, different cultural attitudes toward disclosure, different institutional risk tolerances. For now, that framework doesn't exist, so NASA is navigating this alone, or at least without a clear roadmap for how to handle it. They're making decisions in real time about an unprecedented situation, while being watched by the world and constrained by multiple overlapping policy frameworks. The broader point is that space governance is evolving. The rules that worked for routine operations are being stress-tested by anomalies, by increasing commercial activity, by international competition, by public demand for transparency. 3i Atlas sits at the intersection of all these pressures. Whatever NASA does or doesn't do will likely influence how these policies develop going forward. But NASA isn't just dealing with abstract policy questions. They're also dealing with concrete, recent examples of how anomalies in Earth orbit create similar tensions. The next section will explore one of those cases. Part 13, Anomaly in Earth Orbit Surveillance. February 9th, 2025. The US Space Force's Space Surveillance Network tracks an unusual radar signature in geostationary orbit. The object appears suddenly, wasn't there on previous scans, and shows reflectivity characteristics that don't match known satellites or debris. For 48 hours, it's a mystery. Space Force analysts run the signature through their catalogue. No match. They check with satellite operators. Nobody's launched anything new to that orbital slot. They look at debris models. Nothing explains it. Then it disappears, just vanishes from tracking. One pass it's there, next pass it's gone. No decay trajectory, no indication it deorbited, just gone. Space Force releases a brief statement on February 11th. Anomalous radar return observed in geostationary belt. Object no longer tracking. Likely instrumentation artifact or debris fragment below persistent tracking threshold. No threat to operational satellites. That's it. 2 sentences. No details about the specific characteristics. No radar data released. No images. Just a generic statement designed to acknowledge the observation without saying anything substantive. Why the minimal disclosure? Because Space Force operates under different rules than NASA. Much of what they do touches on national security. Their surveillance network exists partly for science, but primarily for military purposes. They track satellites from potential adversaries. They monitor for anti-satellite weapons tests. They provide early warning of threats. When that network detects something unusual, the default assumption is that it might be military relevant. Could be a new Russian satellite with stealth characteristics. Could be Chinese testing orbital rendezvous capabilities. Could be debris from an unannounced test. The military considerations come first. But here's where it gets interesting. Amateur satellite trackers also saw something weird during that same time window. Posts on specialized forums discussed unusual brightness events in that region of sky. Observers in Australia, South Africa, and South America all reported seeing something briefly. Their observations corroborate that something was there, even if they couldn't identify what. So you have official acknowledgement that's minimal, combined with amateur observations that are more detailed but less authoritative. And in the gap between the two, speculation flourishes. What was it? Why did Space Force downplay it? What aren't they telling us? Compare the speed and transparency to 3i Atlas. Space Force went from detection to public statement in 48 hours. Minimal information, but at least acknowledgement happened quickly. NASA is weeks into 3i Atlas with no comprehensive statement. Why the different timelines? Part of it is mission difference. Space Force exists to protect US space assets and monitor potential threats. Quick acknowledgement with minimal detail fits their operational needs. They need to tell the public, we saw it, we assessed it, no danger, without revealing capabilities or intelligence methods. NASA exists to do science and inspire the public. Quick acknowledgement with minimal detail doesn't fit their mission well. The public expects more from NASA. They expect explanation, context, education. A 2-sentence statement wouldn't satisfy anyone. But the contrast highlights how even close-to-home anomalies get caught in these delay versus explanation cycles. If Space Force hesitates even for orbital objects that might be military relevant, why wouldn't NASA hesitate even more for an interstellar visitor that might have much bigger implications? The February anomaly also triggered internal review within Space Force and NASA. Was there any coordination needed? Did the timing of the Earth orbit event and 3i Atlas being near its closest approach create any connections worth investigating? Almost certainly not, but someone had to make sure. Someone had to check whether there could be any relationship between an interstellar object and an orbital anomaly. That checking takes time. It requires cross-agency communication. It requires people in different bureaucracies talking to each other, sharing data, ruling out unlikely but not impossible scenarios. And while that's happening, neither agency can fully disclose what they know because they're still figuring out what they know. There's also the question of precedent. How Space Force handled their anomaly sets expectations for how similar situations should be handled. They acknowledged quickly but revealed little. Does that become the template? Or does the criticism they receive for lack of transparency push future responses toward more openness? Amateur observers were frustrated. They felt like Space Force gave them nothing useful. The official statement didn't help them understand what they'd seen. It felt dismissive, like the agency was saying don't worry about it without actually addressing the observations. But from Space Force's perspective, they did their job. They assessed the threat, determined there wasn't one, informed the public of that conclusion. Providing more detail would reveal surveillance capabilities they're not willing to reveal. It's a different calculus than NASA faces, but it's driven by similar tensions. If NASA hesitates for an orbiting satellite anomaly, if Space Force hesitates even briefly, why wouldn't both hesitate even more for something as unprecedented as an interstellar visitor showing anomalous features? The Earth orbit case shows that hesitation is the norm, not the exception, when something doesn't fit the standard playbook. Every agency has to manage the tension between transparency and operational security, between public curiosity and institutional constraints. 3i Atlas is testing those boundaries at a much larger scale, but the underlying dynamics are the same as what we saw in Earth orbit. Unknown object, unusual characteristics, pressure to explain quickly, institutional reasons to move carefully. These aren't isolated incidents. They're all connected by the same governance challenges, the same policy gaps, the same struggle to balance competing priorities. And they're happening at a time when science itself is under pressure from revolutionary discoveries that challenge existing frameworks. Part 14. Scientific Revolutions Under Pressure. June 23, 2025. A team of astronomers announces the detection of an exoplanet atmosphere showing spectral signatures inconsistent with any known chemistry. The planet, orbiting a star 240 light-years away shows absorption lines that don't match oxygen, methane, water vapor, or any other common atmospheric component. The discovery is based on data from the James Webb Space Telescope. Multiple observations over several months. The signal is strong, repeatable, not likely to be instrumental artifact. But nobody can explain what molecule produces those lines. The paper announcing the discovery is remarkably cautious. Unidentified spectral features detected in transmission spectrum. Possible systematic effects cannot be fully ruled out. Alternative explanations include unknown photochemistry or instrumental calibration errors. Further observation required. That language tells you everything about the scientific culture around anomalies. Even when you have solid data, even when you've checked and double-checked, you hedge. You don't claim too much. You leave yourself room to be wrong without looking stupid. Why? Because scientific reputations are built slowly and destroyed quickly. If you announce a revolutionary discovery and it turns out to be wrong, you become a cautionary tale. Your career suffers. Your future papers get scrutinized more harshly. Your funding applications face extra skepticism. So scientists self-censor, not in the sense of hiding data, but in the sense of tempering language, emphasizing uncertainty, inviting alternative interpretations. It's protective behavior, rational given the incentive structure of academia. But that self-censorship can delay paradigm shifts. If everyone is too cautious to suggest that existing models might be fundamentally wrong, then the field can get stuck. New ideas don't emerge because nobody wants to be first to stick their neck out. The exoplanet atmosphere case is still developing. As of mid-August 2025, several other teams are trying to observe the same planet, to verify or refute the initial findings. That's how science should work. Claim, verification attempt, consensus building. But it's a slow process. It could take years before we know whether those spectral lines represent a real discovery or a measurement error. Compare this to NASA's dilemma with 3i Atlas. The incentive structure is similar. Scientists looking at the data might see things that challenge standard models, but they're reluctant to say so publicly without overwhelming evidence. Because if they're wrong, the consequences are severe. Agency-sponsored science has additional constraints. When you work for NASA or receive NASA funding, you're not just representing yourself, you're representing the institution. Your statements reflect on the agency. So there's pressure to conform to institutional messaging, to not freelance with dramatic claims that could embarrass your employer. This isn't conspiracy, it's just organizational dynamics. People who work for large institutions learn to be careful about what they say publicly. They clear statements with management. They use approved language. They think about how their words will be interpreted and whether that interpretation serves institutional interests. In normal times, this works fine. It keeps messaging consistent, prevents misunderstandings, maintains professionalism. But when something genuinely anomalous appears, those same dynamics can become obstacles to truth-telling. Imagine you're a NASA scientist who's analysed 3i Atlas data and concluded that the observations don't fit natural models as well as everyone hopes. You think there's a real possibility of something extraordinary. What do? You can't just post it on Twitter. That would violate your employment agreement. You can't send it to a journalist. That's probably a fireable offence. You can present it internally, but then it goes into the review process we've been discussing, and you lose control of the timeline. Or you can temper your conclusions. You can write the paper with all the hedges, all the caveats, all the alternative explanations. You can make your actual finding so buried in careful language that it doesn't attract attention. That's the safe path. But it's also the path that delays paradigm shifts. The history of science is full of examples where revolutionary ideas were initially resisted because they challenged dominant paradigms. Continental drift was ridiculed for decades before plate tectonics became accepted. The bacterial origin of ulcers was rejected until overwhelming evidence forced acceptance. Dark energy seemed absurd until the data became undeniable. In each case, the delay wasn't because of conspiracy but because of legitimate scientific conservatism. Extraordinary claims require extraordinary evidence. The burden of proof is high, as it should be. But that high burden creates friction. It slows down the recognition of genuine anomalies. 3i Atlas might be forcing NASA into this exact position. If the data genuinely shows something paradigm challenging, the institution faces pressure to downplay it until the evidence is overwhelming. But gathering overwhelming evidence takes time, and in the meantime, the delays and hedged language fuel suspicion. This is the broader ecosystem in which NASA operates. It's not just about one comet or one anomaly. It's about how scientific institutions handle uncertainty, how they balance caution against openness, how they navigate the space between protecting truth and protecting reputation. The exoplanet atmosphere case will probably resolve one way or another within a year or two. Either the spectral features will be confirmed and explained, or they'll turn out to be artifacts. Either way, the scientific process will eventually work, but eventually can feel like forever when you're watching in real time. 3i Atlas is on a faster timeline. It's moving through the inner solar system now. Peak observation opportunities are happening. If NASA is going to release comprehensive data, it needs to happen soon. After the object gets too far from the Sun, after its activity dies down, after it heads back into interstellar space, the window closes. We'll be left with whatever data was collected during this brief window, and future historians will judge whether NASA used that window wisely. The final section will look ahead to what's coming next, to the upcoming observational opportunities and the questions that remain unanswered. Part 15. Cliffhanger and Call to Watch. 3i Atlas reaches perihelion, its closest approach to the Sun, on September 11, 2025. That's less than 3 weeks from now as of this recording. When a comet reaches perihelion, its activity peaks. Outgassing intensifies, jets become more prominent, brightness increases. If there are any unusual features to be observed, this is when they'll be most visible. NASA knows this. Every major observatory knows this. The James Webb Space Telescope has observation time scheduled. Hubble has already been watching and will continue. Ground-based observatories across both hemispheres are coordinating campaigns. This is the moment. This is when we'll get the best data we're ever going to get about this object. But here's the question. Will we see that data? Will NASA release it promptly, or will it go into the review queues we've been discussing? Will the images appear in public archives within days, or will we be waiting weeks or months while the data undergoes analysis? There are also spacecraft considerations. The Parker Solar Probe, NASA's mission studying the Sun, will be in the inner solar system during 3i Atlas's perihelion passage. Parker wasn't designed to study comets, but it has cameras. If 3i Atlas passes close enough to Parker's trajectory, those cameras might capture images from an angle no Earth-based telescope can achieve. Would NASA release Parker data quickly if it shows something unusual? Or would that data, because it comes from a high-value mission with complex instruments, face even more review than telescope observations? ESA's solar orbiter is also in the neighbourhood. Another spacecraft not designed for comet observation but capable of it if opportunity arises. If Solar Orbiter gets images, ESA's track record suggests they'll release them faster than NASA. We might see a repeat of the pattern from July, where European data appears before American data. Congressional interest is building. The House Science Committee has been monitoring the situation. No formal hearings are scheduled yet, but staffers have been asking questions. If the perihelion passage produces dramatic observations and NASA continues to delay release, expect congressional pressure to increase. Hearings could be called, NASA leadership could be asked to testify about data release policies. There are also rumours, unconfirmed but persistent, that at least one major peer-reviewed journal has papers in review related to 3i Atlas. Those papers are under embargo, meaning the findings can't be discussed publicly until publication. But the fact that papers are in review means scientists believe they have results worth publishing. What do those results show? We don't know yet. But we'll find out when the embargo lifts. Amateur astronomers are planning observation campaigns. With even modest equipment, backyard telescopes can track 3i Atlas and measure its brightness. Those amateur observations won't have the resolution of professional instruments, but they'll be public immediately. No review process, no institutional constraints. Just raw observations posted to forums and social media. If amateurs see something dramatic that NASA hasn't acknowledged, that discrepancy will fuel conspiracy theories. If amateurs see nothing unusual, that might support the natural explanation and reduce pressure on NASA. Either way, the amateur community is going to be part of this story. The final dramatic question, the one that should keep you watching. If NASA's next data release looks oddly edited, if images have regions blurred or cropped, if certain wavelengths are included but others aren't, if the timing seems coordinated to minimize impact rather than maximize scientific value, might that be evidence of something more than routine caution? We're not claiming conspiracy. We're not suggesting NASA is definitely hiding something, but we're saying the patterns matter. If the delays continue, If the releases remain partial, if the explanations stay vague, then we have to ask whether institutional self-preservation has trumped scientific transparency. NASA can't control both authority and truth simultaneously. If they choose authority, if they prioritize institutional reputation over complete disclosure, they might protect themselves short-term while losing trust long-term. If they choose truth, if they release everything, even when it's uncertain or challenging, they risk short-term chaos but might preserve long-term credibility. This isn't just about one comet. This is about how humanity handles the discovery of something genuinely unexpected. This is about whether our institutions are equipped to deal with paradigm shifts, whether our governance frameworks can accommodate anomalies, whether transparency and authority can coexist when the stakes are this high. So here's the invitation. Stay tuned. Pay attention over the next month. Watch what gets released and when. Compare official statements to amateur observations. Notice the gaps between what different agencies disclose. Ask questions. Demand transparency, but demand it thoughtfully, understanding the constraints NASA faces while still holding them accountable. The next update could rewrite how we think about extraterrestrial visitors, or it could confirm that 3I Atlas is just an unusually weird comet, exotic but natural, interesting but not revolutionary. Either way, how we get to that conclusion matters as much as the conclusion itself. September 11th. Perihelion Passage. The moment of maximum observation opportunity. The moment when 3I Atlas reveals whatever it's going to reveal. And then, decision time. Does NASA show us what they saw? Or do they make us wait while review processes grind and speculation fills the void? You're watching a test. Not just a test of astrophysics, but a test of institutions, of governance, of humanity's ability to confront the unknown with both courage and caution. The test is still in progress. The results are not yet clear, but the fact that we're even having this conversation tells you something about where we are as a civilization. We have the technology to observe the cosmos in unprecedented detail. We have the scientific knowledge to recognize when something doesn't fit our models. We have the communication systems to share information globally within seconds. But we also have institutional constraints, political pressures, legal frameworks, and human psychology, all of which complicate the simple act of saying what we see. 3I Atlas is moving. Time is not on our side. Whatever NASA decides, they need to decide soon. Whatever they know, they need to share it before the object moves beyond optimal observation range. The countdown is running, the world is watching, and somewhere in a building where data is reviewed and decisions are made, someone is weighing impossible choices. What they won't show you, that's the real story. But maybe, just maybe, in the coming weeks, they'll show us everything, and then we'll know. Not just what 3I Atlas is, but whether our institutions can handle the truth when the truth is stranger than we expected. Stay curious, stay skeptical, stay watching. The next chapter is about to unfold, and it's going to tell us as much about ourselves as it does about an interstellar visitor that chose this moment, this year, this cosmic alignment, to pass through our solar system and challenge everything we thought we understood about how the universe works and how we respond when the universe surprises us. The telescope images are being captured right now. The data is being collected. The analysis is happening. And soon, very soon, we'll know whether NASA trusts us with the truth or whether the impossible situation they're in forces them to choose silence over disclosure one more time.